All right, in this video, we're going to talk about Chapter 3. Chapter 3 is where we're going to really start to get our hands on some data. What we're going to do in Chapter 3 is we're going to imagine that we have some data set that's been given to us. And then what we want to do is we want to come up with what are some descriptive values of that data set that we can use to describe that data in general. So we want to know if there's like representative numbers of that data set that we can use. And there's going to be a few different ways that we can talk about that. The first way is with what's called a measure of central tendency, or a measure of center. And this is the mean, median, and mode, which I'm sure many of you have seen before. The mean of a data set is really where you just take all the values. Say you have the values x1 to xn. You add them up, you divide by n, which is your number of data points. That's your mean. This notation that I'm going to write is, it's called a sum notation. And again, if a little bit of calculus is going to be present here, you don't need to know calculus for this class, but some of the definitions and terminology and some of the reasoning why things are defined the way they are come from calculus. So if you have calculus, you'll have a little bit better glimpse about why things are defined the way they are. And again, if you've seen anything in calculus, you've probably seen the summation sign already, right? If you've taken calculus in a previous semester anyways. So this sign, this summation here, just means, so this summation sign really just means that you're going to add up all those values and then we're going to divide by n. So that's the mean of a data set. The mean of a data set can be a very useful number for us. It can be representative of all the data. It includes all the possible points that you have. The downside is that it's very susceptible to outliers. So if you have a particularly large value in your data set, that could skew the mean and make the mean a slightly misleading statistic to use to describe your data set. On the other hand, you could also talk about the median. And the median is really, you just put all your data points in order, and the middle number is the median. If you have an even number of data points, you take the mean of the two middle numbers. So if you were to have, let's say you were to have the set 1, 4, 6, 11, here you have 4 data points. Your median would be the mean, or the average of the two middle points, so 5. So here we would have a median of 5. That's going to be our convention for how we compute the median when we have an even number of data points. Okay, so that's the median. The median has a few upsides and downsides. The upsides is that it's easy to compute if your data is in order. The downside is that it actually ignores all your data except the 1 or 2 values in the middle of your data set. That can actually be a good thing rather than a bad thing. So the median is less susceptible to outliers. Whether you have your largest value is, outrageously large compared to all your other values, that's less relevant for a median because you don't care what the value actually is. You just care about the values in order. So the median is less susceptible to outliers in that sense. And that's why the median is often used to describe salaries. If you were to have a CEO who has a salary that's 20 or 30 or 100 times larger than the average worker, including the CEO's salary in the average salary for the company is misleading because that's just going to skew the mean, but it does not skew the median. So frequently when people talk about salaries or when you're talking about anything where there can really be an outlier, the median is very useful for that because it's less susceptible to outliers. Okay. The last thing that we can do to talk about a measure of central tendency is use the mode. That's the most frequent value in the data set. The mode's not terribly useful because the mean and median you can have much better, they're much more descriptive. The mode just isn't quite as useful as the other two. The one good thing about the mode is that the mode actually makes sense for qualitative data, so the data that's not numbers. You can still talk about what's the most frequent value, and so the mode still makes sense there, but otherwise it's really not that useful as a whole, at least compared to the mean and median. I shouldn't say it's not that useful, it's not as widely used as the mean and median there. Okay, so the next example is we have, again, some salaries, and you can compute the mean and the median in the mode of each of these salaries. And they're roughly comparable, right, in your two data sets. I'm not going to really walk through too much of that. I will go through one example later when we do some of these examples by hand. So I'll kind of show you something in a second here. Before we do that, let's talk about skewness in terms of the mean and median. And so if you remember, to say that a distribution is right skewed means that it has a long right tail. Okay, so this long right tail means that it's right skewed. And right skewed data has the characteristic that the median is less than the mean. Okay, the median and the mean, we should define those. The mean is actually defined via an integral. So you have to be a little bit careful here. I'm not going to actually define that yet. We'll talk about that in chapter 5, what the mean is of a distribution. But the mean is defined in terms of an integral. The median is also defined in terms of an integral, but you can intuitively make sense of the mean. Of the median. So the median you can make sense of right away. The median is just going to be the halfway point. Okay, so this is the halfway point, so that the data on either side, if you were to look at the data on either side, it's going to be cut in half. So the median is the halfway point, so that half of the data lies on one side of the median, half the data lies on the other side of the median. Okay, so that's what the median is. That makes sense whether you have infinitely many values or not. And again, the mean is defined as an integral. But the skewness you can define in terms of the median and the mean. So again, if the median is less than the mean, you have a right skewed data set. If the median is greater than the mean, you have a left skewed data set. And if they're approximately equal, you have a symmetric data set. All right. Again, the sample mean has a formula. This is the formula that we talked about before. And that's really all I wanted to say about measures of central tendency. What we're going to do next is let's talk about measures of variation. So what I want to do is I want to consider two basketball teams with different heights in inches. And these basketball teams are going to have, if you were to compute the mean, the median, and the mode of each of these heights, they're all going to be the same. So the mean of each data set is 75. The median and mode of each data set is 76. And yet these two distributions, these two teams, have very different looking sets of heights. And what's different about them is how spread out these values are. Team 1 is much more centrally located together. They're less spread out. Team 2 is a lot more spread out. And so we want to make that quantitative. And there's two ways to make that quantitative. The first is with what's called the range. The range is easy to compute, but it ignores almost all the data. You only need 2 data points. And the range is just the largest value minus the smallest value. And again, it's very easy to compute. It tells you all the, it tells you where your data set kind of lives, like what are the largest and smallest values that you're allowing in your data set or that you have in your data set. It does not give you that much more information though. So it's not super useful. It's just largest value minus smallest value and ignore the rest. When you have 5 data points, the range, it might be a reasonable thing to do. When you have 1 million data points, the range is really not going to tell you much at all, because all it does is it ignores all but 2 data points. So that's the range. Very easy to compute, so we'll talk about it. Not used too frequently. What is going to be used frequently is what's called the sample standard deviation. We'll talk later about the population standard deviation, but for now, the sample standard deviation, and remember the difference between there is you have the population is all of your data points that you're considering. Your sample is some small subset of that population. And so here we're talking about the standard deviation of a sample. That'll be important in a bit when we talk about population standard deviation. So sample standard deviation has this formula. The upsides is that it uses every single data point. And so it's not just going to use the largest and smallest values. It's going to use every single data point that we have. The downside is that it's slightly a pain to compute by hand. It's not really terrible, but it's a slight pain to compute by hand. So lowercase s is going to denote our sample standard deviation. One other thing that comes up is what's called the sample variance. And the variance is s squared. It's going to be that same formula, but without the square root. And the idea with the sample standard deviation is that the larger the standard deviation, the more spread out your data is. The smaller the standard deviation, the less spread out your data is. Okay, so that's what it's going to do, and it tells us how spread out our data is in a quantitative sense. We'll talk about how to interpret that as we go along. So what I'm going to do next is I want to actually go back to our basketball team 1 example and look at those heights, 72, 73, 76, 76, 78. And I want to calculate the standard deviation. And what the standard deviation calculates is how far on average is each height from the mean of the data set. So if you remember, our mean was 75. And we want to know, on average, how far does each value deviate from the mean? And so the formula that we'll use is that one. So we're going to take our data points x sub I. So we're going to take our data points x sub I. We're going to figure out how far are those values from the mean. We're going to square them, add them up, divide by n minus 1, where n is the number of data points, and then take a square root. So it's more computationally involved. It's not terrible. We have calculators, but it's a little bit more involved than just computing the range. So here's how I want to kind of organize our data. And we have, along the top there, you can see that we have our data points 72, 73, 76, 76, and 78. And our mean was 75. So I'm going to write our data points in a column. I'm going to compute what's our data minus the mean. So we have 72 minus, we have 72 minus 75, 73 minus 75, 76 minus 75, and so on. Now, if we were to add up the values, xi minus x bar, oops, what just happened here? Uh-oh, okay. If we were to take xi minus x bar and add up all those values, we will get 0, because sometimes the numbers are less than the mean, sometimes they're greater than the mean. The mean is supposed to be somewhere in the middle, so it makes sense that when we add all those values up, we should get 0. So what we're going to do is we square those values. In squaring, make sure that when we add them up, we don't get 0. We could also take absolute values, but it turns out, again, if you've taken a calculus course, you know that absolute values and calculus don't play well together. So instead, we take the square of those values. So we're going to get -3 squared, -2 squared, 1 squared, 1 squared, and 3 squared. So it's 9, 4, 1, 1, and 9. Add those up. That's going to give us 24. And then the standard deviation is going to be the sum of those values divided by n minus 1, where n was the number of data points. So altogether, we'll end up with square root of 6, which is about 2.44. So about 2.44 for our standard deviation. Okay. And again, the larger the standard deviation, the more spread out the data is. The smaller the standard deviation, the less spread out the data is. And we'll talk about how to make that precise. All right. That's exactly what I just said. There is a computing formula for sample standard deviation when we're doing this by hand. It turns out that if you take the xi minus x bar squared, and if you were to square it, you could algebraically simplify that expression that we had before. And so if you prefer to use this version of the sample standard deviation, that's fine. We're going to use R anyways, or whatever software you like, R or Excel, I guess. And so those are kind of built in already. So we don't really have to worry too much about using these computing formulas. That was much more useful when people were doing statistics by hand, which we're not going to do. So That is sample standard deviation. There's the 3 standard deviations rule, which basically says that almost all your data, no matter what your distribution is, almost all your data is going to lie within 3 standard deviations of the mean. And we can be very precise when we have a normal or a bell curve. So when we have a normal distribution, which is this like bell-shaped distribution curve, we can be very precise about what we mean by almost all. So it turns out that if you have a normal distribution, about 68% of the data lies within 1 standard deviation. So that means that going from x bar plus s to x bar minus s, 68% of the data lies within 1 standard deviation. If you were to do x bar plus 2s and x bar minus 2s, so you were to look at this interval, then about 95% of the data lies within 2 standard deviations. And if you were to do 3 standard deviations, then you would get 99.7% of the data lies within 3 standard deviations on either side of the mean. So if you were to take the mean plus 3 standard deviations and the mean minus 3 standard deviations, you would end up with 99.7% of the data. Okay, and so that is what the standard deviation tells us. And we're going to go back and we'll have a whole chapter all about the normal distribution. It's going to be our kind of our starting point when we actually start to talk about statistical models and how to use those to make inferences in regards to statistical decisions and solving these problems. Okay.